and any laws, any equations that pertain to those particular concepts. And then we also illustrate the use of those equations, those laws and principles and so forth, utilizing some examples. These are numerical examples. And so bottom line, if you look at the first screen here, you see energy mentioned here. So what is energy? Basically, energy is a capacity to do work or perform work, and it is expressed in BTUs, British thermal units. In the US, that's the common unit. Bear with me just one more second. This person is having difficulty logging in. My apologies. All right, that's amazing. We sent everybody an invitation, and they gave us the wrong email address. So anyway, my apologies. So if that person calls again, we'll just have to worry about it later. Okay, so anyway, energy is the capacity to perform work. It's in the U.S. we measured it in BTUs, British thermal units, and across the big pond, and maybe in Canada as well. Not maybe, actually, Canada has already converted quite a bit to metric units. They would basically express it in joules, and where 1 joule is 1 Newton meter. So those are different types of units. Now, mechanical engineering, and which is what thermodynamics is a part of, they essentially in this field, you see that in the U.S. we use dual units in many cases. Some people are very ingrained in some sectors in the use of U.S. customary units, which is what a BTU is, essentially the old British unit. And of course, if you go to Great Britain, they've also to a great extent converted to the metric units, which would be joules. So so you see some of that, and in this particular subject, and as we go through it through the course of the day, you'll see dual units as well. You'll see some of the work, some of the illustrations will be in metric units, and some of those illustrations will be in British or U.S. customary units. So you'll see the dual use of units, and we'll try to keep up with both. And then, most of all, once you do do a problem, and and if you do it in metric units, you can just easily convert at the end of your if that is what you prefer, meaning if that's the unit system you prefer. And I kind of subscribe to that school of preference, if you want to call it that. I like the metric unit a little bit better than the the U.S. unit system for various reasons, primarily because of the equations that are simpler to use with metric units. And then at the end of it, I'll convert it all over to all of the numbers back into the U.S. unit system, and you'll see some of that reflected in some of the problems that we'll do. So bottom line, energy is expressed in BTUs and can also be expressed in foot-pounds or horsepower hours in the U.S. units. And you know, when you see foot-pounds, that also kind of tells you that the work, work and essentially the three concepts: work, energy, and torque. They're almost identical. In fact, I say almost at the magnitude level, they're basically synonymous. Where they torque may differ from the others is that the torque is basically a vectorial entity. It has both to fully define torque, you have to have both magnitude and direction. Other than that, at the magnitude level, torque, energy, and work are essentially identical. And you'll see a little bit of that reflected in when we get into deeper into the thermodynamics equations today. Anyway, here you see in metric units, it's Newton meters. 1 joule is 1 Newton meter, and also energy when you're interconverting, from thermodynamic realm to electrical realm. And one of you mentioned you're electromechanical engineer. So when you're interconverting, you basically you see that when you convert mechanical energy to electrical to mechanical, the electrical component the power in electrical component would be expressed in watts, where 1 watt is 1 joule per second. And you multiply joule per second by time, you end up with joules, which is a unit for energy. So therefore, kilowatt hours is a unit for energy. And and it's common to convert between kilowatt hours and BTUs when you're, for example, when you're looking at a steam turbine based power generating plant in a steam type of power generating system. It could be coal fired, could be gas fired, but basically we're talking about steam turbine, the brake horsepower put out by the steam turbine, basically being converted into electrical horsepower by the generator. So we'll see that actually, that whole process, unfold when we look at the SFEE equation, steady flow energy equation. We'll derive it, and we will we'll actually use it, and as we do a little case study that is excerpted out of a book that I published. And by the way, the basis of this program is, or this particular program is themed after a book I published titled Thermodynamics Made Simple. The book was published, I'd say maybe 5 years ago or so, and so it, of course, if you want to take this process of learning thermodynamics to the next level, the book could be the next stepping stone. And if you are interested in it, you can review it online, and then if you want to purchase it, you can purchase it through the typical, big retailers like Amazon.com or Amazon, and Barnes and Noble, even Target, I think sells the electronic version, even the book in print, but it's online. And Association of Energy Engineers, if you're a member of it, you can get the book through with a discount. So that's where a lot of you'll see a lot of the diagrams and some of the case studies, excerpts of case studies that I've used in this program are actually borrowed from that book. So the other thing that we'll learn when we get into thermodynamics is the concept of specific values. So what are specific values? So here you see specific energy. So what is specific energy? Specific energy is essentially energy per unit mass. And so as such, it is would in the U.S. unit system, it would be defined as BTUs per LBM, or it could be foot-pounds per LBM. In the metric unit system, it would be in kilojoules per kilogram or joules per kilogram. And then this concept of internal energy, the energy contained in a system. When you do thermodynamic analysis, in the U.S. unit systems, it's represented through BTUs, and a metric unit system, it would be joules or kilojoules. A symbol that represents internal energy is uppercase U, and you would represent the absolute internal energy using uppercase U. Now, but when you convert the absolute internal energy of a thermodynamic system into specific energy, what you're doing is you're dividing this the actual absolute energy by the units of mass, and so it would be energy per unit mass, and so that's the difference between specific energy and internal energy, both symbolically as well as in units. So then, as we look at absolute heat in a thermodynamic system, heat that might be added to a thermodynamic system, or heat that is